Hey guys, and welcome to Chapter 19, the second half. This is, or the second part. We are going through Chapter 19, Section 4, and Chapter 19, Section 5. Alright, let's go ahead and get started. Make sure you have your guided notes, your book, calculator, and some good ears, because here we go. It says, you know that we can calculate delta H, or enthalpy, through calorimetry. So how can we calculate delta S in the lab? Well, we don't just have enough time to dive into that right now. You will learn something of this when you take physical chemistry in college. But like I don't know if I've ever told you this, but physical chemistry was one of the hardest classes I've ever had. And basically, I'll tell you that it has something to do with that perfect crystalline structure on the top of page 816 at absolute zero. And basically you use that as kind of a stepping stone to step off of zero entropy. So perfect crystal at absolute zero, and then as you step away from that, we start adding energy. Okay? So it has something to do with that. So in a lab, for now, you just need to realize that delta S has already been tabulated for you. And you obviously just need to be looking for that table, which is in the back of your book. Okay? It's right there along with all of your other enthalpies and everything. It's in Appendix C. And Appendix C for me starts on 1112. Alright? But there's a new term to entropy. Rather than just saying plain old entropy, there's something else. There's molar entropy. So we need to be careful about our units. The only difference between entropy and molar entropy is that molar entropy will have this mole on the denominator, and regular plain old entropy will not. Regular plain entropy is just joules per K. Now molar entropy is joules per mole K. And just so you know, standard molar entropies is anything that's at standard conditions like 1 atmosphere, 0 degrees Celsius, those type of things. We always put this little 0 on there to represent a standard. I'm sure you're used to seeing that by now, but I thought I'd make sure you know. Alright, so here's some interesting things about entropy that I think we better make sure you get. It says, unlike enthalpy, which is, heat energy, your entropies for your elements, remember, like pure elements or things that are like the simplest element, guys, entropy is not 0 for those. So when you're doing those like Hess's law type equations, you're not going to be able to just skip over the elements anymore. Molar entropies of gases technically are greater than liquids and solids, like straight across the board. And of course molar entropy generally increases with the increase in molar mass. We talked about that last class, tried to explain that. And then finally molar entropies usually increase with the number of atoms in the formula. The more atoms you have, the more range of motion that you have. So that's just a quick review. And then this formula, just basically, if you've never seen an epsilon before, it just means sum of. So you're adding up the sum of the molar, and it always stands for mole, of the molar coefficient of all the products, minus the sum of the molar coefficient of all the reactants. So it's just like enthalpy. It's always products minus reactants, and when you're looking at the equation, you have to take into consideration all of the coefficients that were used in the balanced equation. So, for example, I want you to use Appendix C to solve for the following. It says, calculate delta S standard for the synthesis of ammonia from nitrogen and hydrogen. And it says, remember, elements do not have 0 entropy. So I'm doing this as a random sample example. We are forming ammonia, correct? So NH3 is what you are making. You made this from hydrogen and nitrogen gas. The very first step that you need to do is to make sure you balance this. The second thing you need to do is to go to your appendix and look up all of the quantities for all of these items. Okay, so that's what I'm doing right now. I'm flipping there. Okay, so for example, I'm looking at hydrogen. I found it. It's over on the left side of page 1113. You'll notice that delta H formation is 0 because you can't form elements. That's God's job. The delta G formation, we'll get to that. Okay, that's not anything that I'm going to talk about right now. But we do have entropy, the S. That is the only value that you have, which is interesting. So your H value, notice the positives and negatives, do be careful. It is 130.58. And look at your units, joules per mole K. Okay, so here's your hydrogen value. Next, let's find nitrogen. Nitrogen's on the same page, but it's on the right side. Notice for nitrogen, N2 gas, you have 0 delta H, 0 on delta G, but you do have a value for your S, 191.50 joules per mole K. Okay, and then finally the last guy. The last guy, that was pretty much the whole point, is to try to figure out the delta S. Go back to the question real quick. The whole point is to calculate delta S for the synthesis of ammonia from N2 and H2. Alright? So what we're going to do is... we need ammonia. Sorry, my bad. Let's go find ammonia. It's in your nitrogen compounds. Alright, so we got a delta S of 192.5. And it's positive. And this is joules per mole K. Alright, so it's always products minus the reactants. And you have to take into consideration all of the molar values here. Okay, so your products, 2 times 192.5, that's a positive value, there's your products, minus, so here's where we got to be careful, and I'm going to use an extra bracket because we have 2 reactants here. You only have 1 nitrogen, and it's a positive value, 191.5, and then we're going to add that to the molar coefficient of 3 times 130.58. Okay, I hope you see where I'm getting all of that. And obviously at this point we need to switch gears and grab a calculator. Alright, first thing I'm going to do is the stuff inside of the parentheses here. 3 times 130.58. Alright, we're going to add that to the 191.5. The total value of everything in the brackets here is 583.24. And let's go ahead and do 2 times 192.5. Okay, we get 385. Alright, so let's do that now. Minus 583.24. I get negative 198.24 joules per mole K. Alright, let's see if we did it right. Can't remember the answer. Balance the reaction first. Let's see, is the synthesis as a and I forgot, we were supposed to predict the sign before we actually did the math. So think about your reactants. Let me go back to here. Think about your reactants versus your products. Okay, your reactants, you have 4 moles of gas, and then your products you only have 2. You are technically becoming more orderly. And remember, the delta S will be higher. The value for your product or your reactants will be higher than the value for your products. So remember, it always goes like this. Delta S overall is equal to delta S of your products, so final, minus delta S of your reactants, initial. And I told you that this value was going to be larger, higher than this value, because you have more moles. So it makes sense that the value here should be negative. Alright, so we predicted the sign. Here's the formula, filled it all in. You should get negative 198.3. Is that what we got? Triple check. Sweet. Little off. Alright, so, and by the way, I forgot, this is for the entire reaction, so I don't think we should be putting a mole here. Sorry, not molar and entropy. This is just the entropy of the synthesis of ammonia. Period. Done. Alright, coming back. Alright, now the second topic that you learned about was about Gibbs free energy. So we've seen that enthalpy and entropy seem to determine a little bit of the spontaneity. We talked a little bit about that so far. If it's extremely exothermic, it seems to be spontaneous. If the delta S value, if you're becoming more random, what does that mean? Does that mean that you are spontaneous or not? You may need to look that up again. But then there's this guy, Josiah Willard Gibbs. He determined a new formula to help determine whether or not a reaction is spontaneous. So what if, for example, if you have an endothermic reaction, but your products are less orderly than your reactants? That gets kind of tough, right, to determine the spontaneity. So he took everything into consideration. Guys, this is the end-all equation of thermodynamics, I mean. So over here, the sign of G. If G is negative, it's spontaneous. If it's 0, it's at equilibrium. And if it's positive, that means how the equation is written, always as the equation is written, it's not spontaneous. Alright, work needs to be done to make it go. Alright, so again, if delta G is negative, spontaneous. Delta G is 0, equilibrium. Delta G is positive, then it is not spontaneous. Work must be done. Alright, you cool? Moving on. So, free energies of the elements. Now we're switching back. Sorry. Delta G for your elements are just like delta H. They're 0. Alright, there is no spontaneousness for like making of elements unless, again, you're God. Alright, that's the way I think of it. So, it's the same formula for delta G as the other ones, as delta H and delta S. It's always the products minus the reactants. So, the free energy delta G will tell us if a mixture of reactants and products will react in the forward direction to form more products, or in the reverse to form more reactants. Okay, so basically the sign of delta G will tell you if it's spontaneous as the way it's written, and if it is, good, but if it's not, it'll be spontaneous in the reverse direction. One thing that I would like to add is a little tidbit about the term negative T delta S or minus T delta S that is in your Gibbs free energy equation. So, just FYI, when delta S is positive, that's entropy. When that value is positive for a reaction, which means that the final state has greater randomness than the initial state, that means that delta T or negative T delta S is negative. Okay, so when delta S is positive, that term becomes negative. But, of course, when delta S is negative, then that term becomes positive, right? You have two main components to your Gibbs free energy equation, one for enthalpy and one for entropy. So you've got the delta H, which is obviously enthalpy. And then you've got negative T delta S, which is your entropy part. So what does this have to do with anything? Well, remember that the sign of delta G will tell you whether the process is spontaneous, right? So basically, it will depend on both of these signs and the magnitudes. So when both delta H and negative T delta S are negative, then of course your delta G was going to be negative anyway, right? And of course when they're both positive, then delta G will be positive. But what if one of them is positive and one of them is negative? That's tricky. Then that means that the sign of delta G will depend on the magnitudes of those two numbers, right? How big delta H is compared to T delta S. Alright, so generally here's how it goes. Delta H and delta S change very little with temperature. So pretty much the value of T can directly affect the magnitude of your negative T delta S. So just be aware of that. It's a little trick, okay? I thought that this was a really good diagram. This is on page 821 of your text. And this is a great way to think of it. Look at your free energy here. Free energy is going this way. And this is just your reaction quotient, basically where you are in the process of making ammonia. This was our example. So on this side, this would be your reactants. On this side, this would be your products. Right here in the middle, technically you're at equilibrium. And so I just wanted to make sure you understand the values of the delta G. Over on the left side, it would be spontaneous, as it's written, to go towards ammonia. But then on the left side, if you've got a whole bunch of ammonia, it is spontaneous for it to reach and come back and make some more nitrogen and hydrogen. All right? So this is something to keep in mind, that this actually technically is very true about this equilibrium. And ammonia does this spontaneously on its own. So pure ammonia is actually kind of dangerous, because look at what it's making. Hydrogen gas. All right? Anyway. So here are some critical thinking skills I want to make sure you got. So with this formula, we can determine spontaneity. Here's an example. You got H2O solid melting into H2O liquid. What is the sign of your delta H? Is that an endothermic process or an exothermic process? Do you have to add heat or take it away? What is the sign of delta S? You went from solid to liquid. Which one do you think is more orderly? And what does that mean? Finally, as T increases, what happens to negative T delta S term? Now, where did I get that term from? That's from Gibbs free energy's equation. Look at the equation carefully. And then finally it says, you know that if T is greater than 0, the reaction here, as written, will be spontaneous. So, you know that delta G should be negative. Everybody should get that. But this term, negative T delta S, is actually a pretty important term when we talk about Gibbs free energy. This particular term will determine, for most circumstances, whether or not it can make it into the negative region. Remember, if delta G becomes negative, what does that mean? That means it's spontaneous. So this negative T delta S is incredibly important to remember that. That's a little trick that people use to figure out if it's spontaneous or not. Alright, let's keep going. What if? What if we drop T to below 0 for the formation of that water written above? I want you to think about what would happen to this term right here. So what if you have a negative temperature? Do you see what's happening to this term then? It becomes less spontaneous. Alright, do you see that? Delta G doesn't turn negative. Instead, it's going to now be positive. Okay? So a little trick to keep in mind. And now, let's look at some sample exercises. Let's look at 19.6. It says, calculate the standard free energy change for the formation of nitrogen monoxide from nitrogen and oxygen at 298. Given that, they give you delta H, they give you delta S. Alright, so they want you to calculate the standard free energy, and of course they have to tell you at what temperature. So think about all the little puzzle pieces and how you're going to fit them all together, because that's exactly how you need to tackle this problem. First of all, you've got to memorize this formula. There's no ifs, ands, or buts about it. You just have to know this, okay? So your delta H is right here. Now remember, this is delta H standard for the entire reaction. So there is no like per mole or anything on this. They just gave you standard delta H. Next up, your delta S. Be careful, look at the units. It says per Kelvin. That's a huge hint for you that you need to get rid of the Kelvin. Alright? That'll kind of help you develop your own equation. So for us, it's pretty simple. All we're going to do is make sure that we're using the same units. If you have kilojoules here and joules here, you got to make sure that you make the correct adjustment. So the easiest way for me to do this, I don't care how you do it, just make sure that you're using the same unit on your energies, okay? If you use joules over here, you got to use joules over there. If you use kilojoules here, you got to use kilojoules there. Alright? So as you can see, they worked out their work. They've got 180.7. They put their temperature in, multiplied it. They kept it in the joule form, but you see this little conversion here that they did to switch it to kilojoules. Remember that it is a minus sign, and so you've got this right here. So this is 180.7 kilojoules minus 7.4. Correct answer is 173.3 kilojoules. Now, because it's positive, what does that mean? Is it spontaneous or not? Simple question. Remember, if delta G is positive, it is not spontaneous. If delta G is negative, it is spontaneous. It's that simple. Okay? Alright, so sample exercise 19.6 done. Very easy. Alright, let's do sample exercise 19.7. Alright, the question says, use data from Appendix C to calculate the standard free energy for the following reaction at 298 K. Alright, we're going to tackle it the same way that you tackle delta H as you tackle delta S. So it's the same formula, you just have to look up all of the stuff, okay? So the first one I'm going to look up is P4 and you'll find it on the top of 1114, and make sure that you guys are looking up the correct one. This is P4 in the gas form, and delta G looks like it's 24.4. So this guy is 24.4 kilojoules per mole. Okay. Cl, chlorine, element, doesn't count. You could waste your time to look for it, but it's a 0. Alright, let's look for the other guy. PCl3, make sure you find it in the gaseous form. PCl3 in the gaseous form. This guy is negative 269.6. Make sure you're really careful with your signs. Kilojoule per mole. So now all we need to do is make sure that we multiply our coefficients and do the products minus the reactants. So I'm going to multiply this guy by 4, since there's a coefficient of 4. And then make sure that I subtract that, because it's always products minus reactants. Alright, so these are the little tricks of the trade. So just take 269.6, multiply by 4. Make sure we get the 24.4 in there. Make sure you got negative signs in here, because these are all negative. You should get negative 1102.8. Exactly right. Kilojoules. Done. By the way, since it's negative, what does that mean? Duh! It's spontaneous. Alright, guys. Pretty simple. Hey, guys. What is delta G for the reverse of the above reaction? Hey, guys, that would mean that you would have to flip the equation over and make it products minus the reactants, right? So you got to think about that one. Be careful here. Let's look at what they said for part B. Okay, so for this guy, the reverse, thus reversing the reaction changes the sign of delta G, and it just changes it into the positive region. So even though you have a negative number up here, for the reverse reaction it'll be the same number, just positive. And you could check yourself by doing the work, but that's pretty much how it goes. Alrighty. Finally, let's do 19.8, sample exercise. This guy starts on the bottom of page 823. It says estimating and calculating delta G. It says in section 5.7 we used Hess's law to calculate delta H for the combustion of propane gas at 298 K. So here's your example. They gave you delta H. It says without using data from Appendix C, predict whether delta G for this reaction is more negative or less negative than delta H. Okay, this is why I wanted you to analyze that negative T delta S value, because it's really a very good practice to do some of the critical thinking on these before you get an answer. So here we go. It says in part A, we must predict the value of delta G relative for that of delta H on the basis of the balanced equation. Okay, so here's our plan. Just remember that the formula for Gibbs free energy has this delta H minus T delta S. You've got your temperature that they gave you for the problem right here. It's 298, so we're in the positive region on our T. Alright, so all we need to do is to predict the sign of our delta S. And you guys are pretty familiar with how to figure out the sign on delta S. Look at the balanced equation. You've got how many moles of gas on your reactant side? 6. How many moles of gas on your... Oh, that's a liquid. Interesting. So you've got 3 moles of gas, 4 moles of a liquid. I'm wondering if you can kind of guess based off of what you see up above. Alright, so obviously you can use your book to read on, but we need to make sure that you understand where we're getting this from. It says, we see that the reactants consist of 6 moles of gas, and the products consist of 3 molecules of gas and 4 molecules of liquid. Okay, the number of molecules of gas has decreased, right? Decreased a lot. And it says, by using the general rules we discussed in section 19.3, we would expect a decrease in the number of gas molecules to lead to a decrease in your entropy of the system. So technically, for us, The products have fewer accessible microstates than the reactants do. So if you're still confused about all of that, I would recommend you go back and reread 19.3. Alright, so we've decided that the products are more orderly than your reactants. What does that mean for you? That means that the value of your reactants are high. Remember, delta S is equal to, the overall, is equal to delta S final minus delta S of your initial. These are your final guys, and we decided that this value was going to be low. This right here, these are your initial. We decided that these are going to be high. So everybody, what is the value of your delta S? Final, remember, low, initial, high. You should have a negative delta S. Alright? So what does that mean about that negative T delta S value? Alright? Says we therefore expect delta S and therefore T delta S to be negative numbers because we are subtracting T delta S, which is a negative number. We would expect delta G is less negative than delta H. So look at this. This value right here, you are subtracting a negative number, correct? If you're subtracting a negative number, that means it's positive, correct? So that makes this particular value right here, this H, basically these two should be an opposite sign. If this guy is going to increase on the positive area, then this guy should go a little bit down, should be a little bit less. This value is typically opposite of your delta H. So if this guy is increasing, this guy will be decreasing. Alright, so second part. Use data from Appendix C to calculate the standard free energy for the reaction at 298 K, and of course, is your prediction from Part A correct? Well, gosh darn, I hope it is. Alright, so now we get to use your appendix. I'm going to go ahead and scroll down. Okay, so using the balanced equation, look at all the work that they did. They always put the products before the reactants. So look up your delta G's for CO2, H2O, C3H8, and do you really need oxygen? Do you really need to find the delta G for O2, gas? No, that's going to be a 0. Okay? So, remember all of the coefficients. You had a 3 in front of the CO2, a 4 in front of the H2O, and make sure you look up the liquid water value. And then remember that they also want the gas value for C3H8. Fill it all in, and when you do your math correctly, be careful with your positives and negatives. You should get negative 2108 kilojoules. It says, notice that we have been careful to use the value of delta G formation for H2O liquid, because remember there's two of them. There's like one for the liquid and one for the gas. And as we predicted, delta G is less negative than delta H. What was the delta H value? Do you remember what it was? Negative 2220, and we just calculated negative 2108. Alright, because, let's see. I would recommend that you guys try this practice exercise on the bottom, and if you do that, I would like you to not only predict what they are, but I would like you to explain why the delta G is more negative. And if you do that and calculate it for real using the appendix, I'll give you a little extra credit. Okay? Alright guys, that's pretty much it for now, and I'll catch you next time, okay? Ta-ta!